This lecture is going to be on the use of phasors and equivalents, Thevenin equivalents and Norton equivalents. And because you've seen this material before in circuits 1, I'm going to approach this material quickly by first doing a review and next working a fairly complicated example, and last working through a collaborative problem, giving you plenty of time to do your own work and see if you can solve it as I go through. The concept behind Thevenin and Norton equivalent circuits begins with the idea of a linear circuit. And those are the circuits we've studied so far that are composed of voltage sources, current sources, resistors, capacitors, and inductors. And because we're working in the phasor domain, we're going to represent these capacitors and these inductors as a generalized impedance Z. And what Thevenin and Norton equivalents say is that you can take any linear circuit of any complexity, any order, any number of resistors, capacitors, inductors, voltage sources, current sources, and you can represent it, if you've got exactly two output terminals shown here, as everything in that circuit boils down to a single equivalent source. I'll call it VOC for V open circuit, with a series, I'm drawing it as a resistance, but because we're in the phasor domain, it's really an impedance. Generally, we call impedance as Z. I'll call it Z equivalent. This is the Thevenin, or equivalently as a Norton, which is a current source. I'll call that I short circuit, and it has a parallel Z equivalent, and that's the Norton equivalent, such that the two output terminals here are these two output terminals, and all the other components inside that linear circuit are all boiled down to that single voltage or current source with a complex impedance. So the question is, why would you want to use a Norton or Thevenin transform? And all undergraduate textbooks in circuit theory talk about these transforms, but very few say why they're actually useful or why they're used in the real world. And here's why. In the real world, you don't have perfect voltage sources or current sources or anything. You have real world parts, and they've all got Thevenin or Norton equivalents. So as an example, let's say you want to have a battery that powers a project, and you design your battery to be a 3-volt battery, and you go power your motor with this 3-volt battery. And the specifications of the motor is that when you give it 3 volts, it turns at 100 RPM, and when you hook it up, it doesn't work. And it should, because it's a 3-volt battery, 3-volt motor. The reason why it doesn't work is because you didn't find the Thevenin equivalent of either component. If you had, you would discover that that 3-volt battery that you were using only supplies 3 volts in an open circuit, but its true Thevenin equivalent looks like this. And that motor has a Thevenin equivalent too, and its Thevenin equivalent looks like this. And you might say, oh, come on, a motor doesn't have a voltage source in it. It actually does, because you know that you can run a motor as a generator. If you rotate the shaft of a motor, it generates a voltage. It's called back EMF. And what this particular motor is saying is that it generates a back EMF of 0.01 times whatever its RPM is. So if you want it to run at 100 RPM, it's going to generate a back EMF of 1 volt. And so you'd have to make sure it gets 4 volts. But you're not even supplying it by 4 volts because there's resistance in the windings shown here, and there's resistance, and there's a resistance inside the battery here. And so, of course, when you analyze this to try to find the resulting voltage across the motor, it will not be 3 volts, even though you connected it to a 3-volt battery. Thevenin models are really important in the real world, and you must understand how to find them. So that brings us to the next question, which is, how do you find them? There are two main methods. The first is experimental. The second is theory. Now, as you can imagine, it's the theory one that the bulk of undergraduate textbooks talk about and nothing else. And we're going to devote an entire another video to how to find it in theory. But the experimental one is actually fairly straightforward. You're going to find it by having two measurements of your circuit. Here's your circuit. I'll draw it twice because it'll be two different types of measurements. Your first measurement is you'll measure the voltage open circuit. You're not going to connect anything to the wires, and that will tell you what your VOC is in your Thevenin equivalent model. And your second experiment is you will short the output terminals, and you will measure the current that flows when you short those terminals, and that will be the closed circuit current. And now you only need to do one other thing, which is use Ohm's law to divide VOC divided by I short circuit. That will give you ZEQ. And it's that same ZEQ that you would put in series for the Thevenin equivalent or in parallel for the Norton equivalent. I'll just abbreviate it here. If you find one, you can find the other just by doing a source transform. And you might say, hey, how do I remember that it's the voltage that I remember open circuit and it's the current that I measure short circuit? And the answer is those are the only parameters that make sense. You can't measure closed circuit voltage because a short circuited voltage will always be zero. Same thing for your open circuit current. That would always be zero. So the only two parameters that make sense to measure is open circuit voltage, closed circuit current. You divide them, you find ZEQ. And with those three parameters, you have everything you need to write your Thevenin equivalent or your Norton equivalent. That's how it's done experimentally. Now let's open a new board and talk about how it's done in theory.